Saxon Advanced Mathematics. Lesson 42. This is a good one. This is a fun one. We're going to talk about conic sections. We talked about these briefly in Algebra 2. It's kind of theoretical, but let me explain it to you, and I'm going to explain it the same way I did last year. Do you know what a butter sculpture is? It is when a restaurant or like a place that does fancy buffets, maybe like a hotel restaurant, gets a huge, ginormous chunk of butter and they get it really, really cold, and then somebody with these skills sculpts it. They take knives and they carve out some sort of beautiful artistic shape. Let's say a swan. So you have a giant swan made out of butter, and you keep it in the freezer, and then right when your party's beginning, you bring out this lovely butter sculpture of a swan, and it decorates the table. And I don't know if people actually use it. I'm just thinking if I've ever been someplace that actually has one, and I've seen people digging their knives in. I think it's just like an object of art. But as you can imagine, it's made of butter and it's super cold. We today are going to work with some butter sculptures, but ours are not going to be in the shape of swans. We want to imagine that someone has created, let's say they're about half a meter tall, so it's standing on the table in front of us. It is a shape called a conic section. That's the name of this shape. It's the shape that you get if you take, pretend this is a perfect straight line, my marker. Pretend it's a perfect straight line. I take it in the middle and I'm fixing it by a single point in the middle. Obviously my finger is too big to be a single point, but pretend please with me. And then let's say that there is a motion that starts moving the ends of my perfectly straight line. Do you see how they're creating a circle? I mean, kind of, right? It's kind of a person with a marker and a phone. I realize my technical effects are shoddy, but if you can imagine that my marker is this line and my fingers are holding it there, and that's the circle that I'm making with the top, and so there's a circle with the bottom of it too, then you can imagine a conic section. This whole thing is called a cone, and the two halves are called naps. We're not really going to use that word, but I thought it was fun, so I'd share it with you. And so this is our butter shape. Our butter sculpture is made into what is called a conic section, and this is called a circular cone. The conic sections are going to be the shapes that we're going to cut. So let's draw 4 of these though, because our local ice sculptor has kindly prepared 4 for us, and they're sitting in the freezer walk-in on one of those really nice stainless steel trays that restaurants and hotels always have. There's 4 of them, 4 for each of us, so we don't have to share, because what we're going to do is going to be really fun. Okay, now, I don't know if you've ever felt silverware that comes directly out of like an industrial dishwasher, not just like a home dishwasher. You've probably felt that, but I'm talking about the kind that comes out of like a restaurant dishwasher. They're super hot, and we've got a bunch of butter knives. You know, the kind that you set at the table. Not a sharp knife, but just a butter knife. But they are red hot. And when we pick up those knives and push them into our butter sculpture, it is just gonna give way. That frozen butter is just gonna melt underneath our knife, and we're gonna get the smoothest, most beautiful cuts. The first thing that we're gonna do is we're just gonna cut straight sideways through one of these naps. And then we're gonna take this, you can just take the top part off and look at that, or we can look at the part underneath the cut. Either way, But when we look at it, what we're gonna see is a circle. Does that make sense? I'm gonna write it here. When we cut straight through the nap, we will get a circle. If we take the second sculpture, the second circular cone, then cut it, instead of straight across, this one we're gonna cut at an angle. And when we take the lid off that one and look either at the bottom of the cut side or the top of this side, what we're going to see is an ellipse, which is a fancy name for oval. When we were in kindergarten, we said oval. Now we're too cool for school, so we say ellipse, but it's just an oval. All right. Now, what if we take the third sculpture? I hope you're having fun with this because I love putting these knives through this butter. This time, we're gonna cut at an angle like this, and we're gonna basically chop that little tip off. When we take it, this is open at the top, so when we take it and look at that shape, again, either on the, we can look on either side of this cut. We can look at the side of this piece or we can look at the side of this piece. What we're going to see is what we call a parabola. All right, and then our last one, we've come to the end of our chopping session. This time, we're going to go straight down so that we cut off two pieces, right? Here we went on an angle and we just cut off one, but this time we're cutting off two. And so when we look at, we can't really look at the two pieces very well, but when we look at this part of the sculpture left, we're gonna have two shapes like that, right? This will be the shape going up and this will be the shape going down. This shape is called a hyperbola. All right, these four shapes are what we call conic sections. All right, they're the figures formed at the point of intersection when we make these four cuts. If you would like to see John's Super Professional conic sections that have a little bit of shading so they look slightly more dimensional, I didn't take the time to make super fancy 3D drawings for us. And his butter knife cuts, he shows the plane of the cut. It's a little bit easier to see the technical, but you can see his shapes turn out just like ours. So take a look at this page if you like. It's 301 if you want to jot it and look at it later. But we've captured the essence of this. So what we're going to be studying is this one and this one a bit now. We've already talked about parabolas. I think we're going to come back to those. We won't spend much time on hyperbolas, but we will look at these three. We're going to look at this one later in this lesson. I want to point out to you that the circle and the oval are not functions. Remember our vertical line test where if you can draw the line down and it passes at most one point in the figure, then it's a function. Ours fails, doesn't it? Because we could draw a line that hits twice on the circle. So a circle is not a function, but it is a conic section. That's kind of weird, isn't it? That's kind of weird. So sit with that. Now we're gonna go on and we're done with the butter knives and the melting butter now. Let's just put all that stuff on our trays and push them toward the waiters and we'll forget about that. And now we're gonna go sit down and talk about a circle. Now you probably feel rather comfortable with the idea of circles, and I'm not here to upset that, but I am gonna put some fancy words to things and maybe change around the way you have thought of circles in the past. The definition of a circle is this. A circle is the location of all the points on a plane that are the same distance from a point called the center. Okay, that is the center. Now we're going to measure out, and I'm just gonna guess, we're gonna measure out 4 points that are roughly the same distance from that point to the center. Pretend it's perfect, okay? In real life, this would be perfect. And then we're gonna just keep measuring points that are exactly the same distance from the center to the point. And in the end, we will connect all of those points, and we have made a circle. So this is the center, and then we can say all points are equidistant. There's a fancy word. Equidistant from the center. There is a fancy math definition for you with a $5 word thrown in. All right, you already knew that. You know this distance has a name too, right? It's called the radius. Oh yeah, we've been doing that for a while. So this is a fancy definition, but, and I'm just gonna write that up here. Definition of a circle. I'm not gonna write all that, that's enough. You know it's a circle. Now I'm gonna tell you some news that might not make you happy. There is a thing called the equation of a circle. Of course there is, right? Wouldn't be math if we didn't have an equation. Now, before I give you the equation, I want to draw you another picture of a circle, and I want to label a few things on it because these are going to show up in the equation. All right, the center of the circle can be anywhere. It could be on the origin of our graph, but it can be floating anywhere off on our graph that we want. But the center, the name of that point, we're going to call HK. All right, for whatever reason, geometry and algebra dudes got together and decided that should be the letters we use for the center of the circle. I know, I think they're kind of crazy. And then they picked any random point on that circle, right? We know they're all the same distance. It says right here they're equidistant. And then we're gonna call our point that we're working with XY. That is a comma, not a 1. XY. All right, now we already talked about this too. The distance from the center to the point, we know what that is. That is R, and we call that little puppy the radius, right? We've been talking about that for a long time. You know what a radius is. Okay, so given these labels that we're putting on the different parts of our circle, here's the equation of a circle. Okay, we're starting with X and Y, and then we're subtracting the center point from each one of them, right? X is adjusted by H, Y is adjusted by K, and we're saying that you square each of those differences, you add them together, and that should equal the radius squared. Huh, I mean, that seems really random, doesn't it? Who knew? This is what we call the standard form. Of the equation of a circle. This is nice because it's easy to graph. Because if we were looking at this, we could see, oh, there's the center. We'd have to take into account this minus sign drama. We'd know that that's the center, and we'd know that's the radius, and we could graph it from there. However, oftentimes, we may want to have this in what's called the general form. And in order to get to that, we simply expand the binomials. And we're gonna do this in just a minute, so don't worry if this makes no sense right now. See how this says squared and this says squared? Well, if we had the standard form, we would have numbers in there, and to get it into general form, we would actually do this squaring. We would do the multiplication. So I'll show you that in just a minute. But these are the formulas. This whole page is just turning into a lovely puffy cloud of wonderful things to know. And like I said, we are going to be fooling around with circles for a while here. So memorize and make sure you know what the points come from. Okay, let's do a problem. We can't just fool around with butter knives and call that math. I mean, we can, but let's do more. 42.2, did we do 42.1? No, where's 42.1? There it is. Find the standard form of the equation of a circle whose center is at, oh, this is just John trying to get us to develop the formula. We don't really know how to, we don't need to do that. I'm just looking to see. He just basically developed the formula through a problem. We don't need to do that. So let's go on to 2. You know I don't like to skip examples. So if I skip one, it must be really dumb. Find the standard form of the equation whose radius is 4 and whose center is at -3, 3. Then write the general form of the equation. Okay, so let's start by remembering the formula for the standard form. It is x minus h squared plus y minus k squared equals r squared. Now, here's a question that a lot of students get tripped up on, and I have to think about this really carefully too. We know that the center is point HK, but it's really easy to get confused when you're putting them into the standard form here. Which one goes with the H, which one goes with the K? I know if we see it written down, it's a lot easier, but if it's just floating in your head, sometimes you go, oh my gosh, which one's which? X and K both have crossing over in their shapes. They don't belong together. That's too much of a good thing. H and Y have too much of the rounded scoopy shape. Too much of a good thing if you put them both together. So we mix it up. We put X, the crossy shape, with the rounded shape, and then we put the rounded shape with the crossy shape. That's how I remember. Take it to the bank. Okay, so what we're gonna do is we're gonna plug in these values, and we're gonna be real careful with this because the formula has a minus. So this is gonna become X plus 3 quantity squared plus y minus 3 quantity squared equals 16. John goes back and forth on this. Sometimes he likes to write 4 squared, sometimes he writes 16. I'm gonna go back and forth and do it both ways. You can do it however you like. All right, so there is the standard form of this circle. That's cool. Now John wants us to put it into general form. So to go to general, square the binomials, or that's what I said before. I said expand the binomials. Multiply, expand, square, they all mean the same thing. Just get rid of the parentheses. Now at this point, I hope that you can square binomials in your head. If you prefer to write it out and do it written out, that is absolutely fine with me. But I do challenge you to get your mental math skills bumping, and I'll remind you of what we can do. The first one is going to be x squared. The middle term is going to be this one plus itself. So plus 6y. and I'm sorry, x. And then the last term is going to be that times itself, right? And now over here, I have a terrible problem. I always mix up my x's and y's, so you'll have to watch me on that. And just yell really, really, really loud if I make a mistake, okay? So then I'll hear you and I'll fix it. Y squared, again, we add this to itself, minus 6y plus 9 equals 16. Okay, so now we're all expanded. Now the way we want to organize this is we want 0 over here. We want to turn this side to 0, and then we want to get these in order. I'll show you. It's easier just to show you than to try and explain it. X squared plus y squared plus 6x minus 6y, and then we're going to subtract the 16, right? So we'll have plus 9, and then we'll have minus 16 as the third part. Those will cancel. So that's positive 18 minus 16 is going to be plus 2 equals 0. This is the general form. Okay, so we put it in order. Just a second, I'm trying not to make a huge mess. X squared, y squared, xy, plain number 0. All right, that's the way the general form should look. I mean, we've done a lot harder, have we not? We have. We have done lots harder. Okay, I think that's, yes, that's the end of this. That's the end of our circle business for now. Now I want to change gears and blow your mind a little bit. Exponential functions. There's something about exponential functions that makes everybody's brain turn to jello, and I'm here bound and determined to help you win the battle against exponential functions. If your brain does not turn to pudding when you're with these, congratulations. I'm very proud of you. If it does turn, it's fine. We'll kill it. We'll firm this up. Don't worry. Okay, exponential functions are functions that have the variable in the power, right? A classic example, I'm just gonna kind of do a little bit of a remix on this. This function is going to be y equals 2 to the x. The variable is in the exponent. That's what makes it an exponential function. Now, here's the cool thing about all exponential functions. They all cross the y-axis at this point. Well, pause until we start getting fancier, okay? But the basic ones, and I'm going to explain later in this lesson which are the ones that are fancier than this. They cross at the point 0, 1. And the reason for that is because this is our function, right? So if we use 0 for x, this will be 2 to the 0. Anything raised to the 0 power is 1. So this is always going to be the right point. Now, when our base is greater than 1, this side is always going to be the asymptote. And I Googled it to make sure that I was saying it right, because asymptote doesn't seem like the right way to say a math word. But it is. So there you have it. This side always just trails back when our base is larger than 1. It will look like this. Then we just find one more point on this side and draw our curve going up, and a really easy one is to choose 1. It'll be right about there, right? I'm using my blue lines, and I just approximate that. This will then become 2 to the first power, and that's 2. So we can put our second point right there, and that's good enough. John almost always refers to these as sketching the graph of the exponential function. We're not trying to get real fancy here. We're just trying to get close. All right, so when our base is greater than 1, and our exponent is the variable, this is pretty much the way it's going to look. This point is red hot, unless what happens that I'm going to show you later. But what if the base is less than 1? What if y equals 1/2 x? Again, there's our variable in the exponent. That means it's an exponential function. And we're still going to have the glory, though, of this point 0 and 1. It's still going to be a winner for us, because anytime we put 0 in as the exponent, we're going to get 1. So this point is still on our radar, except when the base is smaller than 1, that means the asymptote is over here. Like that. These lines technically never touch. I cannot draw with that level of precision, so you just have to work with me. All right. So now we want to find 1 point over here. So let's try, just as we tried 1 here, let's try -1 and see what happens. So this would be 1/2 to the -1. That means it's going to trapeze that 2 up. So that will become a 2, but it's negative because of this minus. This minus sign does not affect the sign of the number. This one is the one that affects the sign of the number. This minus sign is just the trapeze that flips the 2 up to the numerator. The minus sign lives on. So this is going to be, wait. No, I want this to be +2. You're probably seeing oh, this does not have a minus sign. Our function is positive. So the only minus is in the exponent. That flips it up. That makes it a +2. So our point is right there, and it goes like this. All right. When I put -1 in, it only affects the exponent. For some reason that I cannot explain, I chose to put a minus sign there. That's wrong. So this is +2 because the only minus is there. It flips the 2 up, and now we have +2. So this is the way functions look when the base is less than 1, like we had 1/2 here. Now, up till now, John's been kind to us, and he's kept these expressions, these functions that we're graphing, fairly simple. He has not made them too crazy for us. What we're going to do now, though, is wrestle with some problems where John has made things a little bit trickier for us. So let's try the first one. 42.3. And John asks us to sketch the graph of the function y equals 3 to the -x. What? 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 What do we do with that? Well, I agree. That's a bit of a mess. So what we're going to remember is our power rule. If we've got a base and we're raising it 1 power and then another power again, then we can multiply those together, right? That means that we can take an exponent that's 2 things multiplied together and we can separate them. So in this case, I'm just going to show you. I do not expect you to know this. It's going to be 3. We're going to raise that much of it first to the -1 and then to the x. See how I took the -x and I separated it into 2 parts? I shoved the x on the outside because that can stay there when we're done. I'm going to use that -1 and I'm going to simplify this base, and then we'll be able to graph. So when I go and make that adjustment, it's y equals 1/3 to the x. Hallelujah, that's something I can graph fairly easily. This is a nightmare. This is pretty much the same as this. So I feel pretty comfortable graphing that. This is the final form of our function. And now all we need to do is graph it. And I'm just gonna squish it down here. I don't have a lot of room. I know it's gonna cross at 0, 1 because they always do. I know because this base is less than 1, the asymptote is gonna drift away over here. And I know that if I choose x equals 1, y will equal, no, I need -1, don't I? It'll be 1/3 to the -1, which equals 3. So my second point will be there. Make sense? When your base is greater than 1, choose +1 for your test, your one last point. When your base is less than 1, like in this case, choose -1. And that will give you a nice, easy point here, right? So here, when it's greater than this, we want to choose +1. And when it's a fraction, then we want to choose -1. That may help you keep that straight in your head. All right, so this point is 0, 1, and this point is -1. Whoops, I said -1, but I wrote the wrong thing. Let me just start over. It's -1, 3 is that point. All right, and we got it right here. That's what negative's hard to see. All right, so remember those 2 rules that will help you stay on the path. Okay, we still have a couple, just one more? No, 2 more. And the hard part of these is we're gonna be challenged in this process here where we've got a funky looking exponent and we're just gonna practice breaking that down so that we can get a function that we can live with. Ready? Okay. Example 42.4. These are really hard problems, you guys. If you're following along at all, you're doing a fantastic job because these are tough little cookies. Sketch the graph of the function y equals 1/2 2x. Okay, we remember again, if this power rule is what saves us. Right? This is what we're living for because this allows us to factor this is one way maybe you can think of it, or break it into 2 pieces, which is what factoring is. So I know I want the x to be left on the outside because then it's just a nice simple exponential function. So what I'm going to do is I'm going to rewrite this so that we'll square it first, and then we'll raise it to the x power. So that means my function is y equals 1/4 to the x. And let me just double check how John writes these. Yeah, because we want to imply that this x exponent relates to the whole function, we should put parentheses around it. Otherwise, it looks like we're just raising the 1 to the 4th power. All right, so when you have a fraction, it automatically gets those. All right, there it is. Now we're gonna do a little graphiola. You know how I feel about graphing. I don't like to put in more details than we actually need. So I keep it simple. There's that point 0, 1. We know we're gonna need that. We know our base is less than 1, so we're gonna trail this way. I'm gonna label this point because it's always a hot one. Now we're going to choose one more point because this base is less than 1. I'm gonna let x equal -1, and that means y is gonna equal 1/4 to the -1, y equals 4. So that's our second point. 1, 2, 3, Oops, only I have to bring it out. So it's there, and there is the sketch of our graph. And I do like to see this, you know what would make me even happier, is if you wrote your second point like that very clearly so that I can see that's the second point that you choose. You could write it over here as well. Okay? I know this one, if you're paying attention, I know you're gonna have that one in the right place, and then I wanna see that you calculated this one. Okay, last problem for this lesson. Oh, I'm so sad, it's already over. I'm gonna start on a fresh piece because I don't wanna squish. One of my resolutions for this math year, this school year, is I'm trying to write bigger and be a little bit neater so it's easier for you to see. 42.5, ready? This one's, oh, it's so scary looking. Y equals, where'd it go? There it is. Y equals 1/2. Okay, we know the parentheses are there to make sure we know that the exponent relates to the whole thing. Minus x minus 2. Dios mio, what are we gonna do with that? That's not two things being multiplied. That's two things being subtracted, which could be thinking of we're adding a negative. So we're not gonna be able to use the power rule because that's when there's multiplication up here. We need to go all the way back and use the product rule, right? Because that's the one that has addition in here. So what we're gonna do is see that in our example, just to break this down, if this helps you, I'm gonna say that the m in our model is negative x, and the n in our model is negative 2. So I'm gonna write the base times itself, right? Those are like the x's. I can write that over here too, just to help it be understood. And this is gonna be, one of them I'm gonna multiply by negative x, and the other one I'm gonna multiply by negative 2. Whoa, that's really weird, isn't it? That's very, very weird. Huh, all right. Well, this one, we know we don't want a minus sign up there. So I'm gonna break this apart the way we did before. By multiplying, I'm gonna make it 1/2 to the minus, well, I have to put parentheses, to the minus 1, and then all of that goes to the x, right? I'm splitting apart the minus sign and the x in this step, and I can use power rule because this is being multiplied. This was being added, so we had to switch to the product rule. Ay, ay, ay. Aren't you glad I made you memorize these so long ago? I bet you really didn't, but I bet you've got them now. Okay, so this will be able to simplify. Let's do this one. This is a lot easier because for this one, the minus flips the 2 up and then we square it, so it's just a 4, right? 1/2, we use the negative sign to flip it, the 2's in the top, we square it, there's the 4. Okay, and then we'll do the last step of simplifying here, and it's the same thing. The minus sign flips it, the 2's up top, we raise it to the first power, that's just 2, to the x times 4. That is our function. That's correct, but we usually write the constant first and then the exponential piece. What the actual heck? This is correct. Now we're gonna try graphing this. Now, remember how I told you that 0.01 would always be our friend? Here's the exception to the rule. We're multiplying our exponential function by a constant. So that 0-1 relationship gets messed up. 0 is still gonna be a really good choice for x, and we're gonna use it, but this is drama. This is big drama. Okay, so let's start graphing. And we're going to kind of feel our way into this. Remember, John's telling us to sketch. And so we're just kind of feeling our way in. And I told you we can't start with 0, 1. It's not going to work. So let's start with a table. And I'm going to make it fairly big because we may end up playing with a lot of different options. I think we'll be okay though. All right, so let's try x equals 0. Remember, this is x, this is y, and this is 4 times 2 to the x. So this is going to be 4 times 2 to the 0 power. 2 to the 0 power is 1. 4 times 1 is 4. So the first point that we can graph is 0, 1, 2, 3, 4. Okay, so we can see, we know the base is greater than 1, so we know it's going to go this way. What we're looking for is this point where it will be, where it changes from the asymptote this way to the actual interesting part of the curve up here. So we want to find the place where y is equal to 1. All right, now if we were overachievers, we would calculate the inverse function and then push 1 through it. But you know what? We're not overachievers. We're not trying to change the world here. We're trying to just come up with a simple way to do this. Now, 4 times, I'm trying to think if there's an easier way than to just guess into it. I'll show you how to guess into it. But we want y to be 1. So we think, okay, how could we manipulate these numbers? We know it's got to be 4 times 2 to the something. What number could we put up here to make this turn out to be 1? Well, I know that 4 times 1/4 will give me 1. Is there any way we can turn a 2 into a 1/4? Aha! What if it was -2? Do you see my reasoning here? Even if you never would have guessed this yourself, if you can follow what I'm saying, you're golden. -2 as an exponent up here is going to take this, flip it down, and square it. Then it's going to become 1/4. 4 times 1/4 equals 1. There's another point. So, -2 and 1. This is the interesting part of the curve, and this is the floppy little asymptote that just chills down there. Just looking, John has some nice bold face, but I already told you what he said, and that is, if there is a constant that's being multiplied times the base with the exponent, if you've got a dude like this, then the 0, 1 rule goes out the window and you have to find this point on your own. This is -2, 1. All right, so my best advice to you, I need to think of a way to calculate that that's easier, because this is just kind of feeling your way through the numbers and trying to guess what it would be. Which works, but that's annoying too sometimes, isn't it? So let me see if I can come up with a better solution for that. But you know that when there's a constant being multiplied by your base with the exponent, then the 0, 1 rule is off and you have to use more brain power. 42 is done. Yay! Good job. Where are we? I want to tell you that lesson 43 is one of my all-time favorites. I really, 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 really like it. And it's going to bring a lot of things together for us and help us figure some stuff out. It's usually, maybe not the very first time you do it, but this concept is kind of a light bulb concept that most students go, oh, I see. Okay, guess what? I'm done. Thank you. Goodbye.